Hello everyone. So this is where we left off last time. We were talking about conditional PMFs, and we showed how they relate when the information is presented to us as tables. Okay? Which, by the way, reminds me a little introduction to statistics. So remember these examples of conditional probabilities we did down here? So these two numbers, right? We can see that females tend to choose iOS, the Apple operating system, 80% of the time, while males only 70% of the time. Okay, and now the question is here, is this difference really significant? Does it really mean that women choose Apple more than men, right? And that's the kind of question that we'll be able to answer with statistics. So right now we see two numbers, obviously 0.8 is greater than 0.7, but the thing is, since these are random variables, right, because next year I'm going to take the same survey, I'm going to get different numbers, right? So statistic accounts for that, accounts for all possible samples, right, and gives you answers that are much more general than to one particular sample, right? So in this sample, yes, females use more iOS than men, but in general, we don't know if that's true, and that's where statistics will help us. Okay. So now let's talk about the multiplication rule that we saw in chapter 1. Now, this is the PMF version, right? Remember that in this chapter, mostly all that we're doing is using a different notation about the one in chapter 1, right? And the multiplication rule, if you recall, was P of AB is going to be the conditional probability, so A given B times P of B, right? Or there's always two versions, B given A times PA. So that's that multiplication rule. Now, in terms of our notation here, these two equations are equivalent, okay? So here we have the conditional probability, here we have the conditional probability, and then times the marginal, and this would be the marginal in this case, all right? Okay, and similarly, if we computed the marginal of x in this case, right, we would have this summation, and this equation right here would be the analogous of the total probability rule that we saw in chapter 1. Now here we just call it calculating the marginal, right? But underneath you can see we recover kind of the same result. Okay, now let's talk about independence. And again, I hate to repeat the same sentence first, always, but in chapter 1, we already know that independence is, right, the intersection of two. They're independent if is the product of their individual probabilities, right? And again, that comes from the multiplication rule, remember up here, because when they're independent, turns out that this guy right here is just P of B, if they're independent. All right, so the equation right here is the same, just with the different notation, right? So good thing the concept's the same. Bad thing is that now we have a different notation, which has a lot more symbols if you look at it. But okay, the concept is again that the joint probability would be the product of their marginals, okay, of the individual random variables. And that's how we're going to answer the typical question of are x and y independent. So we're just going to check if this equation is true or not. If you find that in one case it's not true, then it means they're not independent. All right, very good. So let's talk about how do we actually calculate probabilities in these types of examples. The general rule that never fails is this one. Okay, so if you plotted an XY scatter plot, I guess, and then you had your joint density defined in each point on this plane, right? And then the point is that each question that can be asked about X and Y can always be translated into a region in this graph. So abstractly, it's just any region like that. So here we're asking the question, what is the probability that X and Y fall in this region? A, right? And all we're going to do is simply identify this region, which might be the trickiest part of the problem, and then simply add up all the probabilities that fall inside this region. So remember, we have to discretize our, so imagine this is a grid, right, of points, like in the first picture of this chapter. So we're only going to consider these probabilities shown inside the area. And if you want a 3D, right, so this is P of X comma Y, so the joint density. These are all, little probabilities that stick up like that. Okay? But that's the concept. So you have a question, and then you have to translate the question into an area in X, Y. And then we just simply add all those areas. Sorry, all those probabilities inside the area. Okay. Finally, we're not going to use it much, but this is the definition of cumulative joint joint CDF. Okay, it's probably X less than or equal to A and Y less than or equal to B. Okay, so let's do some examples. As always, please try to do them all. I'm just going to do the ones that, the best ones, I guess. Let's do this one. It's about independence. Okay, so we're given this data, right? So there's 4, 6, and 6. That's the data we're given. And then the question is, what should be the value of X right here such that gender and year in school are independent? Okay, so how many sophomore girls must be present if gender and class are to be independent? Okay, now this is an unusual question because you don't typically get to choose what your PMF is, right? But here we're just testing for independence, making sure that we know what independence is. So the first step is to write down the data that you have, and those are the numbers 6, 4, and 6 in this table. Right? And this is the joint PMF. The body of the table, right, is the joint PMF. And then X is the unknown. I'm using X. I know it's a bad choice. It's not a random variable or a realization of one. I guess it could be. Anyway, so we're solving for X, right? So what is the value of X such that these guys are going to be independent? So the condition of independence, remember, is that the joint density at any point there has to be equal to the marginals. All right? Which means, for example, and you can take any point in the body of the table. Let me take this one. So that's my joint value P of X, Y right here, right? And then that has to be equal to the marginals. So it has to be equal to this entry times this entry, but in probabilities, okay? Now, if these are to be probabilities, right now they're just counts, but obviously this equation needs probabilities. So the way we do it is we divide by the total sample. So if every number we divide by 16 plus x, which is what the parentheses should be there we have probabilities, and you need to do it everywhere. So everything divided by this 16 plus x. All right, so I use the shorthand. All right, so every entry you divide by that and you get probabilities. Obviously this cell would be 1 after you divide it by itself. Okay, so let's take the entry at 4. Okay, so that entry is 4 divided by, I can write it down now. It should be equal to the marginal of x. So let's say that's this one. 10 divided by, again, 16 plus x times the entry for this one, right? The row total and column totals are your marginals, which is the same. So I'm just going to square it. Okay? And then you can do the math and solve for x. And you'll see that x equals 9. So it turns out that if you have 9, then these two random variables of gender and class will be independent. Okay? All right. Let's do this one. This is a good one. So here we're giving the joint distribution in the form of a table. Remember, the joint distribution is always the body of the table. And here we have the marginals. So this would be the marginal for y, and this is the marginal for x, right? Why? Because this value is the sum of all these numbers, and you're summing across x. Okay, so here the question is part A, what is that probability? Okay, and this is a typical question, right? Where we have to figure out what is the area A in this equation that we use, right? This is the never fail method to compute probabilities. Okay, so in this case, the condition is that y minus x less than or equal to 2. So A is defined such that this, okay? So here, this first table right here is kind of a xy scatter plot, if you will. If this is your y-axis and this is your x-axis. Okay, so it turns out that the area where this statement is true, right, corresponds to this upper triangle right here. Okay, so in this case you don't need to draw the XY diagram, but alternatively you just see where this equation is true or not. There's not so many cells, right? There's just, what, 12? So you can do that. So this is your area A, and all you do is we add up all the probabilities inside this area, which are shown in the second table right here. This is the same PMF, right? If you go up and down, it's the same numbers. It's just highlighted so that the ones in blue are in the area A of interest. And simply you just add those all blue numbers up and you're going to get 0.62. Okay, then the question in part B is, what is the conditional distribution at y given x1? Right? Okay, so the question is this probability. If it's so given that x equals 1, what is that probability that y would be between 2 and 4? Okay, so whenever you have a conditional probability, then you have to compute the conditional distribution. Okay, and the conditional distribution, remember we did it last time in this, remember this example, right? Where you simply, you focus on one column, whichever is the one given to you, and then normalize. By normalize, we mean that the sum of all these probabilities have to add up equal to 1. And that's what we do here. So we only take the column with x equals 1. Let me erase this real quick. All right, so we only take the column at x equals 1, and this is our new sample space. So we're going to divide everything by 0.43 such that the total column would be 1. All right, and this is what we took the original joint probabilities and divided by that column total of 0.43. Okay? And once you have that, then the probability that 2 is less than y less than or equal to 4, right? It's simply, you're going to highlight the ones that are where this is true, right? So I guess this and this, not much. So 0.9 plus 0.15 divided by 0.43, and that's going to be your answer. Okay? Make sure you write down those questions to discuss it during lecture time. All right, the next ones are pretty similar. Yeah, please go through them. We can discuss them, of course, in class. All right. Now let's see the formulas of expectation with two random variables. You'll see that they're the same with one random variable. Remember, with one random variable, it's just, the usual formula, g of x times p of x, and x in the whole sample space, right? So it's the same thing. We're just adding 1 comma y here, and then another summation for y here, and then comma y everywhere. So pretty straightforward generalization of the expected value. And then conditional expectation, we don't need to be afraid of. It might be intimidating name for some reason. But it's the same as regular expectation. The only difference is that we're using a conditional distribution, such as the one we just used in the example with x equals 1. Right? Once you have the conditional distribution, then the same formulas apply. Conditional distribution is just like any other PMF in this case, right? So you're going to have, and again, it's the same formula, right? You sum across the values of x right now because y is fixed. Y is fixed equal to little y. And that's and we're using the conditional distribution x given y right there. Okay. Now we've discussed the concept of the expectation being linear in the context of one random variable. Remember we said e of a plus bx, capital X, is a plus b expected value of x, right? In that sense, we say that it's a linear operator. But now when we have several random variables, okay, so we have here a collection of random variables. from 1 to n. Okay, so the theory that we've been looking at for 2 random variables extends very straightforwardly for n random variables. Okay, now we're not going to go through all the details of that. We're just going to look at the expectation of terms that involve several random variables. Okay? All right, and it turns out that since it's a linear operator, it comes inside summations. So the expected value comes inside summations like that. Okay, which is a very convenient property. And we're going to use it a lot. Okay. Now, please go through this proof and let me know if you have questions during class tomorrow. Okay, but should be good. So this establishes the result for 2 random variables, and of course we can do it for many. Let's do this one. Using the fact that we know that expected value is linear, let's compute the expected value of the sum of 2 dice rolls. Okay, so very simple. X1 and X2 are the results of the 2 dice rolls, and then since it's linear, the expected value of the sum is going to be the sum of the expected values. And we already know that the expected value of 1 dice is 3.5, so the total would be 7. Okay? No magic tricks here. Okay, let's talk about indicator random variables as a prelude to the examples that come right after. So these random variables are really, really useful. And these are variables that are 0 or 1, and you defined it to be 1. Typically you call it a success. So you define it to be 1 if the event that you're interested in takes place. Okay? So this is how we define the PMF in this case. So x could be either 1 with probability p. That's kind of the parameter of this random variable. And now p, and the way you define it, is also the probability of the event that you're interested in to occur. Okay, and then it's 0 otherwise. So the PMF is really very simple, right? X, you have 2 values, 0, 1, and with 2 probabilities. One is p, and one is 1 minus p. Right? Like a coin, but one that is biased. Okay, now if you compute the expected value and variances, you would see that these are the formulas we get. So the expected value of x is p, right? Why? Is because we apply the expected value formula, right? An outcome times the probability plus the other outcome times its probability. That's p. And for the variance, we use the shortcut formula, right? So the expected value of x squared, again, is the value squared times the probability times the other values. And we get p 1 minus p as the variance. Okay? Now, what's important here is this one, is that the expected value of an indicator random variable is the probability of success. Okay? So let's keep that in mind when we do these couple examples that follow that use indicator random variables. All right, so there's a very famous problem, the hat check problem, where suppose that n people leave their hats at the hat check. Okay, and then so they go to a party, they have a good time, and then when they want to go home, they go to collect their hat, but they are randomly returned. Okay, so n people go, and people leave their hats in the hat check, And then when you leave, you're going to be given one at random, which may or may not be yours. And the question is, what is the expected value of the number of people that get their own hat back? Right? So here we're going to use indicator random variables. Right? We're going to define xi, right? And we're adding indices now, right? So I is going to be one of n people. So xi if is going to be equal 1 if person I gets its own hat back. Now, this is my event A, right? And I define it as best fits back, right? So this is event A in the previous definitions, right? Okay, and 0 otherwise. Now, the probability of A here, it's important because we needed to evaluate those expectations. Okay, so again, there are n hats there. Then once you go, they're going to give you one at random. So it's going to be at random from the n hats. So the probability that you get your own hat is going to be 1 over n, the number of hats. Okay? All right, and then that's pretty much all we need because the number of people that get their own hat back, we're going to call it x. All right, and x is simply the summation of the xi's. Right, now this is very important. Okay? Because again, xi's are either 0 or 1s. So if you take the sum, it's going to give you how many people got their own hat back. That's kind of the usefulness of these indicator random variables. Right? First, it was that the expected value is the probability. And second is that when you do the sum of many of these, you get almost always the relevant or irrelevant variable for your problem. Let's say that. Okay, and that's pretty much it, right? Because then we apply expected value here. We apply expected value. Let me change colors. Expected value of x. So we know that summations come inside. So that's, sorry, expected value comes inside summations. So you get expected value of xi. We already know that this guy is P of A, right? Which is 1 over n. Right, so you got the sum of 1 to n of 1 over n, which is 1. Okay, so on average, only one person will get his own hat back. All right, a lot to unpack there. Okay, so yeah, that's the same solution. Please do this one on your own and we'll discuss it if you have problems. Awesome. Okay. Now, let me define these two facts before we talk about covariance. Okay, so it turns out when you have two independent random variables, x and y in this case, it turns out that the expected value, okay, of the product of two functions of x and y, so g of x times h of y in that form, turns out that they're going to be the expected value of one times the expected value of the other, right? It's like the linearity property where the expected value comes in summations. Here, when x and y are independent, the expected value also kind of comes in products like that. Okay? Right, because here you have the expected value of a product, and here you have the product of the expected values. All right. So, but that only happens if they're independent, okay? That's a very key concept here. Again, here's the proof. Please let me know if it should be pretty straightforward as well. All right, so the main step here is that, so that's the definition of the expected value, right? With the joint density, but since they're independent, then the joint density is the product of one marginal times the other marginal. That's kind of the meat of this proof. All right, and now fact 2.6 is a special case of 2.5 in the case where the functions are simply x and y. Right, and we have this very important property for independent events, independent random variables, I should say, that the expected value of the product is the product of the expected values of each. All right, excellent. And now we talk about covariance. So covariance is very similar to the variance. In fact, they're related, and is defined as follows. So that's your formula. So let me just right off the bat tell you the relationship with variance. So when you compute the covariance of x and x, if you replace in the definition, you're going to have x minus e of x times x minus e of x, right? Which is squared. And that's the definition of variance. So covariance of a variable with itself, it's the variance, okay? So you can think of the covariance of a generalization of the variance when you have two random variables. Now, the problem is that the interpretation it's different, okay? It's not concerned so much with the scatter that you see with respect to the mean, but it's more related towards how linear the relationship between x and y is, okay? Okay. So, as usual, we have a shortcut formula. The proof is very similar to the other one. Okay, and just as a check, you can see, so if you did the covariance of x and x, right, such as in here, let me do it here. So e of x, y is just e of x squared, right, if it's x and x, minus e of x times e of x, which is e of x squared. So it checks out, right? It's the same. Okay, so if you take a look at the shortcut formula for the covariance, you can see that we have these two terms that we just talked about right here, in fact 2.6, for this very same reason, right? So you see that e of x, y is the product of the e of x and e of y when they're independent. So when these guys are independent, it turns out that the covariance is 0. Right? Again, it's because these two guys are the same when x and y are independent. Right? Now you got to be very careful that the converse is not true. So saying that the covariance of two random variables is 0 does not guarantee that they're independent. And we'll see examples why that happens. Okay. All you can say when that happens is that they are uncorrelated. All right. So, yeah, whenever you measure covariance and it's 0, it doesn't mean they're independent, okay? The other way around, yes, if they're independent, then they are, they have a covariance of 0. Okay, now remember the coefficient of variation, it was so good because it's dimensionless. Here we have a similar parameter, which is the correlation coefficient due to Mr. Pearson. And simply divide the covariance by their respective standard deviations of x and y, like that. So the good thing is that it removes all the units, and the other thing is that it can be shown that it's bounded by -1 and 1. So the correlation at most can be 1, at least can be -1. So at a glance, you're able to say variables are very correlated or not so much, just by seeing how far away from 0 they are, I guess. Okay? So typically covariance and correlations are very related, like that. And always we prefer dimensionless units. Dimensionless variables, should I say. Very good. So let me try to give an intuition of what the covariance represents. Okay, and I already said at the beginning, it measures how linear these variables are. Okay, now to get an idea why that intuition is like that, let's consider that we take a sample, okay? So we're gonna do like a sample approximation of the covariance. So, and this is doing statistics, kind of. So we collect a sample, and a sample is just a collection of pairs of points, x1, y1, x2, y2, etc. Okay? Now, these guys can fall anywhere in this graph, right? Let's say that's the case, right there. So let's say that's x1, that's y1. So for each point, we have the coordinates. And then, given the sample, we can estimate the mean values. So that's a mu of y and mu of x, right? And remember, mu of y, mu of x are the same as expected value of x and expected value of y. They're synonyms. Okay. Okay, so that's the definition of covariance, first line. The second one is the same. We apply the definition of expected value of a function, right? The function is the product of these two parentheses. So we add up that function times the joint distribution, the joint PMF. Okay, and expected values are like averages. So when we take samples, the way to approximate the expected value is by taking the sample average. So adding up all those numbers and dividing by n. Okay? And the numbers we're going to add up, let's call them CI, which is actually the function that we're taking the expected value to calculate the covariance, right? Is this parentheses times this parentheses, which are the deviations from the mean of each observation, right? So for example, let me take this point right here with another color. Okay, so for this point in red, right, the first term xi minus mu, so it's this distance, and then yi minus mu would be the negative of this distance, right? So we're going to do this for all the points, and we're going to sum them, and then take the average. Okay? Now, the reason we're doing this, we want to know the sign of the CIs. Right? That's why we have it here. Because, all right, so in this quadrant right here, you see that the sign of CI is negative because we're multiplying this length that is positive with this one that is negative, right? So that's the only reason. And if you do that for all the quadrants, then you're going to find this pattern, right? That here and here we have positive values of CI, and here we have negatives. Okay? And this is the best intuition I can give you. Because if you have points, let me put a random sample now with black points. Let's say that we have this situation. So that's one observation, boom, boom, boom. All these points. Okay, so those are the observations, and that's where they fall. Now, we could get, just by looking at the picture, we could get an idea of the sign of this sum, right? Because we're adding up all the CIs. So since most of the points are in the quadrants with where CI is negative, right? We have like 10 points versus only 2 points where they're positive. You can say that most likely the covariance would be negative in this case, okay? Because again, most points fall in these two quadrants. Okay, and of course, conversely, if they fall mostly in the positive quadrants, then the covariance would be positive, etc., etc., etc. Okay, so that's the intuition of the covariance, is based on the quadrants where they fall, the sign that should tell you what the sign of the covariance is. Okay, so these are few examples to give you an idea of correlation in this case, right, which goes from 0 to 1, sorry, negative 1 to 1. These are all positive correlations, so from 0 to 1. So when there's no correlation and then you take a sample, sorry. Okay, so when the correlation is 0 and then you take a sample, so they're not necessarily independent, but you should see mostly a shotgun like that. So no particular patterns. Now, when it's 0.4, you start seeing, so it's positive, so most of the points fall in these quadrants, right? This one and this one, where the CIs are positives. And then 0.7 is already pretty strong correlation. And again, it's because they're mostly here and here. And then 1, which is a rounding error, this should be 0.99 or so. You already see kind of the pattern, right? So rho equals 1 would mean a perfect straight line, okay? Because that's what covariance or correlation measure actually, right? When correlation is 1, it means that it's a perfect line fit. Now, for the negative correlations, we have the same patterns, right? But they go downwards now, okay? So it's related to the slope of the relationship. Now, the common mistake is to think that correlation or covariance give you an idea of how strong the relationship between the two variables are, which is not quite correct because it's not any relationship. It has to be linear relationship. So these are examples of that misunderstanding. So for example, this one, there's the correlation is 0, but yet there's a very strong relationship between the two. The problem is that that relationship is not linear. It's a parabola, right? So if you do the calculations, then you're going to get 0 for this covariance. Same thing here. If you have a sine or cosine type relationship, although the relationship is perfect, right? for a value of x here, you know exactly where the value of y is going to be, which means that they're clearly not independent, right? Yet the covariance is 0, or correlation is 0, right? And same thing here. Now this one is very high because there's a high kind of linear component to this figure. Either there or I guess, yeah. Right, so there's a linear relationship, yet it's not perfectly linear, right? So, and this is why correlation equal to 0 doesn't guarantee independence. These figures are the best explanation of that, right? Especially the ones that with very low correlation. There's perfect relationship between the two, but it's just that the relationship is not linear. Very good.